So today we're looking at some definitions and looking at the law of reflection, as well as some laws that go along with refraction. Okay. So to start out with some basic definition work. When we use the term incidence, we're referring to the incoming ray of light or the incoming sound that's about to hit a surface. So for the picture that we have here, this dark line would represent the surface of our material. It could be water, it could be glass, we're not sure yet. So as light comes in from the sun or some other source, and it travels towards that surface, we would refer to this incoming beam as being an incident ray. And I like to think of the word in to remind me that it's the one that's moving in, or the first thing that's happening. Some of that light is going to bounce off back up to the sky where it came from. And when we refer to something bouncing or moving backwards in the direction that it originated, we're talking about a reflection. So when something reflects, bouncing back. But not all of that light will reflect. Some of the light will continue along its pathway. But we'll notice that rather than traveling in a straight line like it should, it gets bent or shifted into a different angle. So this bend or this shift is what we call refraction. So refraction is the bending or shifting of light due to a new medium. And again, that medium could be air, could be water, everything. So as the sun's light comes in and hits the atmosphere, that air will cause it to shift a little bit. Each color of light will shift a different amount. So blue light will shift a little bit. Red light, a little bit more. Green light, kind of in the middle. Okay? And those amounts of shifting is what relates to the colors of the rainbow as the sun's light hits water. The colors that we get at sunrise, sunset, and the blue sky throughout the day all relate to the ability of this light to bend in specific directions and specific pathways. So before we can talk about the laws that we have, we need to get some basic measurements. So we're going to measure the angles that we have for different values on this picture. As an initial note, when we measure angles, we're going to use the notation theta, and that's going to measure the angle from the normal. In physics, when we refer to something as being normal, we refer to it being perpendicular to the surface. So if this is my atmosphere, or my surface of the water, or the surface of a piece of glass, perpendicular to it, this dotted line here would represent the normal. And so as we start our measurements, we're measuring from that normal line. It's going to be our initial point, essentially our 0-degree angle. And then we can work from that normal back to the incident. I could work from that normal up to my reflected ray, or from my normal and to my refracted ray. Again, so the notation of the shorthand, rather than having to write angle of incidence, is we're going to use the theta and I to represent incidence. Over here we're going to use, again, theta for angle, and since reflection and refraction both start with the letter R, we tend to write out reflection. And that allows us to abbreviate refraction as just the R. So when we're using our protractor, I want to line up the zero line of the protractor, so this bottom line of the protractor, with that normal line. So I'm going to start out by taking my protractor and having the vertex, or the center point here, where my arrows all meet as well. But again, I want to twist that protractor so that the normal line, or my red line on that protractor, is lined up. So the normal and my protractor are in line with each other. So now I'm able to read that actual value. So this first ray here, this interior angle, I've got two numbers to look at, the small numbers and the big numbers. So I need to ask myself, is this a small angle or a big angle? So this curve that I drew is definitely an acute angle, so I'm going to look at the smaller set of numbers. So I've got 10, 20, 30, 40, not quite to 50, so I'm reading about 49 degrees for that angle of incidence. If I take my protractor and I spin it around, again, lining up that zero with the normal line, and then I can track out and figure out what angle or what number this one's at. So again, 10, 20, 30, 40, this one's right about 50. So my angle of incidence I said was about 49. And I'm measuring this one to be about 50. If I measure perfectly, they should come out equal. That's what we're going to refer to as the law of reflection. But obviously we are going to have some human error that goes along with just your ability to measure, making sure we have the vertex, everything like that. I can also measure the angle of refraction down here on the lower end. And again, it's an acute angle, so I'm going to look at these smaller numbers. So I've got 10, definitely not quite to 20. Looks like I'm at 18 or 19, even 18.5 if I want to be specific. So I had about a 50-degree angle over here. And here I'm at about 18.5, 19 degrees for that refracted angle. So as a matter of rule, what we call the law of reflection is that everything should be equal when it comes to these flat surfaces. So my angle of incidence should always equal my angle of reflection. And again, that does rely on us being able to measure accurately, but that's what we're looking for. We also have some laws that are going to go along with refraction. So if I were to compare this 49-degree angle that I started with to this about 19-degree angle that I finished with, then I could say that my angle decreased. Or in layman's speak, we would say that it bent towards the normal. Now this is going to happen for a specific reason. So I started out and I was in air. And I hit some other surface, some other thing, whether it's water, a block, glass. I'm not exactly sure what the medium is, but I know that it's something other than air. And air is about as least dense as we can get. So from going to air into this other medium, I'm gaining density, so I'm getting more dense. So when the angle bends towards the normal, or when that angle decreases, it means that we've hit a more dense medium. When we hit a more dense medium for light, that means that we slow down. So that's kind of our first rule. Or if you want to say it the other way, we could say that when if I were to go from the medium down below up to the air, if we went to a less dense medium, then what would happen? Rather than bending towards the normal, we'd go away from the normal. Rather than slowing down, we'd speed up. So in a less dense medium, we speed, and I like to tell my kids up, up, and away from the normal. And I tell them to think about Superman. So Superman goes up, up, and away. So it's a simple way to learn one of the rules, and by default the other one would have to be the other way. With these values we also have, so with refraction down here we also have two equations that deal with refraction. Those equations are going to be Snell's law, where we compare the index of refraction and the angle that it enters the surface with to the index of refraction and the angle that it has once it's entered that new medium. So again, theta refers to the angle. N is an index. Just like in a textbook, index means you look something up. So this usually comes off of a data table or it's provided to you. In our kids' case, we've given them a data table that tells them what this index is. Same thing over here. This is an index, and it's either going to be provided to us, or in this case, since we weren't exactly sure what the median was, this is going to be what we're solving for. This is our variable, and we have the angles. So I'm going to pull that information off of my picture. I have an angle of incidence up here, and I know that I started in air. I also have an angle of refraction down here, but I'm not exactly sure what medium I'm in. So if I wanted to solve this out, then I would go to my data table, and on that data table it's going to tell me that the index of air is 1.00029. In outer space, that index would be exactly 1 because it doesn't change the speed, so it's our basic number. And then I'm going to use the sine button in my calculator and my angle of incidence, the 49 degrees. I'm going to set that equal to my mystery index times the sine of my angle of refraction, or that 18.5. So I've got my initial setup. Now I just need to solve. Rather than multiplying by the sine of 18 on this side, I'm going to divide to isolate that in. So now this is the equation that I would need to type into my calculator. 1.00029 times the sine of 49. And I want to make sure that I close the parentheses after doing that so that it knows I'm done with the angle. Also, as a quick note, if you are using a personal calculator, make sure that you are set in degrees, not radians, because we're measuring in degrees. And I'm going to divide by the sine of 18.5. And when I do this, I'm coming up with, looks like I was in radians. Let me try one more time. So 1.0029 times the sine of 49. And then I'm going to divide by the sine of 18.5. And as I do this, I find out that my index of refraction is 2.379, so 2.38 would be my index. If I go back to my data table and I look it up, it would tell me that for this picture, my medium, or the surface that I hit, would be a diamond. The second equation that we have for solving for refraction is going to relate how fast that light goes in my new material, in my diamond, to how fast it started out in outer space based on the index. So c is the constant. C is the speed of light in space. And then our v would be our speed in that new matter. So if I was in outer space, my index would be 1. The speed wouldn't change. When I hit the air, it's going to slow down a little bit. When I hit my diamond, it's going to slow down quite a bit. So to solve this problem out, I'm going to use the speed of light. And the speed of light in space is 3 times 10 to the 8th. I'm going to divide that by the index that we solved for earlier, 2.38. And this will allow me to figure out the velocity that my light travels once it's entered into that diamond or into that stone. Now, light, regardless of whether it's in space, in water, or in the diamond, even though it's slowing down in that diamond, it's still light, it still goes very fast. So I'm going to choose to write mine as a scientific notation number. 1.26 times 10 to the 8th meters per second. So we've got some basic definitions about reflection versus refraction. We need to know the laws or the patterns that go with each one. And then we should be able to solve the equations that go along with those laws as well. Hopefully this helps. If you have any questions, please let me know.